Hello and welcome to the science of sleep, where the noise of the day dissolves and curiosity glows like fireflies beneath your eyelids. Here, you don't have to take notes or solve anything, just let go. Let your thoughts float in low orbit, and I'll be your quiet narrator tonight. Breathe gently, as if the universe were exhaling with you. Now, imagine this. Two particles born together in a burst of energy suddenly fly apart, one tucked into a crystal lab in Switzerland, the other sailing invisibly through a satellite over China. Yet somehow, when one twitches, the other responds instantly. No delay, no message, no visible string. It's like watching a mime perform, and the shadow in another room copies every move. Quantum entanglement, they call it. It sounds romantic at first. Entangled. A word stolen from poetry and dropped into physics. But what it really means is stranger. It's not that one particle affects the other, it's that they are the same thing. Or at least, they share a single state across distance. Which of course, shouldn't happen. At least not according to what we were taught in normal life. Things here affect things there, only by contact, by waves or wires or laser beams. If you push a door, it opens. If you text a friend, the signal travels. But in the quantum world, some things skip the travel part entirely. They behave as if there doesn't even exist. And you, lying back in bed, might wonder, how can that be? Well, it starts, not with particles, but with rules. In the quantum realm, everything that can happen does happen, at least until we check. A particle doesn't have a specific place or spin or identity until it's measured. Before that, it exists in a sort of shimmering, maybe a cloud of all possibilities. And when two particles are entangled, their maybes are joined. Let's say you create a pair of entangled photons. You send one to your bedroom and launch the other into orbit. Neither one has chosen its polarization yet, whether it's spinning up or down. But the moment you measure the one beside your pillow, click, it goes up, and instantly the one floating in orbit resolves into down. No wires, no emails, just instant mutual agreement. And the creepy part? It doesn't matter how far apart they are. They could be meters away or across galaxies. Distance becomes irrelevant. Time becomes weird. And you, my dear stargazer, become the witness of something that even Einstein called spooky action at a distance. He didn't like it. Einstein believed in a neat universe, one where objects had properties and space was local, and everything had a cause. But quantum entanglement spat in the face of that neatness. It implied that either the particles were somehow communicating faster than light, or reality wasn't quite real until you looked. Of course, you don't need to be Einstein to feel a little uncomfortable. Imagine if, every time you blinked, your twin across the ocean blinked at the same time. Not because they saw you, not because they heard you, but because both of you were still echoes of a single decision never fully made. There's something childlike about the idea, something almost mischievous. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper trying to prove that quantum mechanics was incomplete, that this strange entanglement was just an illusion masking some hidden gear behind the curtain, that perhaps the particles did know their fate from the start, and we just didn't have the tools to see it. Spoiler, we'll meet that paper again soon. It's called the EPR paradox, and it shook physics. But for now, let's rest in the paradox itself. Because whether or not we understand it, we know it's real. Scientists have entangled photons, electrons, even tiny diamonds. They've measured correlations so precise, they defy any explanation that uses classical cause and effect. No tiny messages, no wires, just a connection that laughs at the speed of light. And here's your weird fact of the night. There are experiments being considered to test entanglement between humans. Not whole bodies, of course, but certain quantum features in the brain. It's still speculative, still blurry science. But imagine, if particles can stay connected across the vacuum of space, could our minds be tugged by similar threads? Don't answer now. Just let that thought linger while the air hums softly around your ears. You're not meant to solve this puzzle tonight. Entanglement is the kind of mystery you fall asleep thinking about, not one you scratch off a quiz. It bends the very shape of reality, suggesting that separation might be an illusion, that people might be more connected than we dare to believe. And maybe that's the real reason this science has become so dreamy. Because while the equations are solid, the feelings they stir are delicate. Awe, discomfort, wonder, loneliness, pierced by a whisper of connection. Tonight, you're lying still, but somewhere, in a darkened lab or drifting particle, something entangled with something else is moving in a way that knows you're here. You wouldn't expect two particles to share secrets like old friends, especially not after they've been pulled apart by kilometers of cable or even the vacuum of space. But here you are still wrapped in the calm of night, tracing the bizarre logic of entanglement. And now, it's time to take a closer look at its strangest implication, the quantum twin paradox. Not the usual twin paradox from Einstein's relativity, the one with the spaceship sibling aging slower. No, this one is somehow weirder, because in this version, the twins don't just age differently, they become different the moment you look at one of them. Imagine you have two particles. Let's name them Lulu and Juno. You entangle them in a laboratory with a fancy crystal and a purple laser. Now you separate them. Lulu stays in your sock drawer, and Juno goes on a ride across town in a fiber optic cable. The entire time, neither Lulu nor Juno has a defined spin. They are, in every scientific sense, undefined but still connected. Then, one sleepy afternoon, you peek into the drawer and measure Lulu. She's spinning up. And instantly faster than the blink you just made, Juno becomes down. It's not that she sees what you did. It's not that she was waiting. It's that the universe just decided, in that exact instant, what both of them were. And here's the unsettling part. This happens even if you wait years to check Juno. The two were like coin flips held in suspense. But not separate flips, the same flip. The quantum state wasn't split between them. It was them. That's the twin paradox at the heart of entanglement. Not delayed aging, but instantaneous agreement. An agreement that makes no classical sense. Let's be clear, no information travels between Lulu and Juno in the traditional sense. It's not like Juno gets a tiny quantum postcard. Hey sis, I landed on up. You're down, love ya. There's no signal, no travel, and yet the results match. This used to sound like magic. It still kind of does. But scientists have gotten quite good at setting up these quantum twins. With careful crystals and lasers and detectors, they've managed to entangle photons, electrons, even small atoms. They've tested the results with statistical rigor, and every time they do, they confirm the same thing. When you measure one entangled twin, the other collapses into the opposite or matching state, just as predicted. Not sometimes, not occasionally, but every single time. And here's the funny bit. Sometimes scientists try to cheat. They set up the detectors so that the choice of what to measure happens after the particles are already on their way. This is called a delayed choice experiment. It's like deciding whether to look at Lulu's hat or her shoes after she's already walked past you. And somehow, your late decision still seems to shape what both Lulu and Juno decide they were wearing. Weird, right? One physicist called it quantum democracy, where nothing counts until someone votes. But in this democracy, everyone's vote is instantly tallied, no matter how far apart they are. And before your brain starts tying itself in sleepy knots, let's ground this in a science fact. Fact check. Entangled particles really do show perfect correlation when measured even across distances over 1,000 kilometers. In 2017, Chinese scientists entangled pairs of photons and beamed them between a satellite and two ground stations, thousands of kilometers apart. The measurements still matched. Even with all that empty sky between them, the twins stayed in sync. So now, lying there under your cozy blanket, you're probably wondering, does this mean the universe is non-local? Or is something else going on behind the scenes, some hidden script we haven't read yet? Physicists have thought of that too. In the early days, some hoped that the particles had hidden variables, some secret pre-agreed instruction set, tucked into their quantum DNA. That maybe Lulu always knew she was up, and Juno always knew she'd be down. That the randomness was just pretend. But no, John Bell, whom we'll visit very soon, proved that if those hidden variables existed, they'd behave differently than what we see in experiments. And they don't. So the universe seems to really be random, and somehow deeply connected at the same time. And now for your odd fact of the night. Some researchers are trying to test whether consciousness itself can entangle with particles. Not by thinking hard at an electron, we're not that desperate yet, but by examining whether human choices in experiments can shape the outcome of entanglement in a meaningful way. It's all theoretical, but it does raise a sleepy eyebrow. So what does this have to do with life? Well, think about it. You meet someone, and for no clear reason, you connect instantly. You think of them, and they message you. You pick up on a mood before a word is spoken. Coincidence? Always. But wouldn't it be fun to imagine that, just maybe, there's a tiny spark of quantum entanglement dancing somewhere between minds? Scientists don't know the answer. In fact, they still debate whether entanglement has anything to say about consciousness at all. But the debate itself is soothing, isn't it? Like watching waves roll over mysteries too big to carry. So let your thoughts drift for now. You don't need to memorize Lulu or Juno. You just need to float with them, entangled across space, doing their cosmic duet in a universe that pretends to be separate, but isn't. You've met the twins Lulu and Juno, and you've watched them perform their eerie mirror act across vast space. But tonight, you're tracing the thread further, down into a phrase whispered through history. Spooky action at a distance. Einstein said it with a raised eyebrow, not a compliment. He didn't like the idea that particles could reach across the void and shake hands without any visible means. To him, that kind of behavior smacked of superstition, like a ghostly pact that defied the common sense of physics. But here's the twist. The phrase stuck, and the spookiness, well, it turned out to be true. So now, tucked beneath your blanket, let's unravel what Einstein found so spooky. In the classical world, the one of apples falling and gears turning, every event has a clear, local cause. If you feel a breeze, it's because something nearby stirred the air. If your phone buzzes, it's because a signal traveled through towers and wires to reach you. But in the quantum world, two particles can seem to influence each other without any such contact. They don't just know about each other. They are part of one shared state. This isn't superstition. It's measurable. Let's revisit Lulu and Juno. Imagine them again, hovering in a lab, each sealed inside a detector. These detectors are separated by kilometers, carefully isolated to ensure nothing could sneak between them. Not sound, not light, not even your nosy neighbor's Wi-Fi. You flip the switch and measure Lulu. Instantly, Juno's state collapses to match or contrast whatever you just saw. Not a second later, not after a dramatic delay. Immediately. It's this immediacy that rattled Einstein. If the universe had any manners, information shouldn't travel faster than light. That's a pretty firm rule in physics. Yet entanglement seemed to ignore it casually, tossing information across space like it was ordering coffee across a quiet table. But wait before you imagine sending interstellar texts via quantum particles. Here's the catch. You can't use entanglement to send messages faster than light. The results are correlated, yes, but they're still random. You can't control whether Lulu spins up or down. And since Juno's outcome depends on Lulu's random fate, there's no way to use it for Morse code or whispered secrets. It's like opening two fortune cookies and finding that the messages match, but only after you read them. You didn't send anything. You just share a creepy coincidence every single time. Here's the science fact to tuck under your pillow. In 2015, researchers in the Netherlands performed a famous loophole-free Bell test. They used entangled particles and extremely fast random number generators to ensure no information could be shared between the detectors. The results? Perfect quantum correlations. Spooky action confirmed. Still, physicists didn't scream ghosts. They just rewrote what action means. You see, quantum entanglement doesn't transmit anything. It's not like one particle does something to the other. Rather, the two particles are parts of a single, non-separable quantum state. They don't affect each other, they are each other, in some strange and flickering way. And that, right there, is the core of the discomfort, because it challenges the idea that the world is made up of parts, that things are separate, that space is a clean, quiet canvas where events happen one by one. Instead, entanglement suggests the universe is more like a tapestry, woven threads crisscrossing behind the scenes, with patterns forming not from parts, but from connection. And you, lying still, are part of that pattern too. You're not just a brain with thoughts. You're made of particles. You are particles. And if those particles ever brushed up against something else, some photon in a sunbeam, some atom in your childhood home, then who's to say you don't carry a thread of that encounter still? Here's an odd fact of the night. Some physicists are exploring whether gravity itself, yes, gravity might be a result of quantum entanglement. Not the pull of mass, but the entanglement of fields creating the illusion of a force. Wild? Yes. Proven? A number. But the thought alone is enough to wrinkle the sheets. So let's return to Einstein for a moment. He believed something was missing. That quantum theory, though powerful, was incomplete. That the weirdness of entanglement was a sign we didn't yet understand the hidden gears of the universe. And who could blame him? Imagine watching someone guess coin flips 100 times in a row, perfectly in sync with another person across the world. Wouldn't you suspect a trick? But no trick has been found, no message, no channel, just perfect alignment without any visible rope. That's what made it spooky. But spooky doesn't mean wrong. It just means reality is underlit. And tonight, with your eyes drifting closed, that's actually kind of comforting. Because maybe, just maybe, you're not as separate as you feel. Maybe there's a piece of you out there, still flickering in rhythm with something or someone else. Not in a way you can measure, but in a way that matters. And scientists? They still debate whether entanglement truly implies a deeper, non-local structure to the universe, or whether it's just how the math shakes out. The debate rolls on, like a soft tide brushing against our old ideas of space, time, and individuality. So let go of the old map. Let your thoughts spread out, like threads in the night, softly tangled in a world where nothing is ever truly alone. You're floating now, suspended between thoughts, between measurements, between cause and effect. And as the night deepens, so does the mystery. What if distance itself is an illusion? You've followed Lulu and Juno, felt the spooky tug between twins, and watched entanglement laugh at the laws of space. But now, things take a stranger turn, because in the quantum world, the idea of location where something is starts to fall apart. Let's say this softly, so your thoughts don't trip over it too quickly. In entanglement, particles don't just ignore distance. They exist in a kind of shared reality, where place is secondary, sometimes meaningless. You might be tempted to picture two dots on a map, connected by an invisible thread, but that's still too classical, too local. A better image? Think of one glove cut in half, not two separate gloves, but one entity oddly extended. Left and right, yes, but not in the way geography usually works. A hole that just happens to appear in two places at once. It's unsettling. You want particles to be somewhere. That's what you've always known. But here, it's not so simple. In quantum mechanics, particles are described by wave functions, mathematical clouds of probability. They don't have exact positions. They have likelihoods. And when particles are entangled, their wave functions overlap, entwined in such a way that measuring one immediately reshapes the other, no matter how far apart they've drifted. You can't draw that with crayons, but you can feel it. You too have known moments where distance didn't matter. A phone call that arrived just as you were thinking of someone. A dream about a person you hadn't spoken to in years. Coincidence? Always. But coincidence, in a quantum world, starts to feel suspiciously like structure. Now here's your science fact for tonight. In 2022, physicists performed a groundbreaking experiment suggesting that quantum entanglement might actually construct space-time. That is, the fabric of the universe, the grid of here and there, could arise from entanglement itself. In other words, the connection comes first, and space is just a byproduct. Not the other way around. Let that simmer, because it's the kind of reversal that makes your pillow feel like a spaceship. If entanglement is more fundamental than space, then location becomes relative, not like in Einstein's frames of reference way, but in a deeper sense, where things are not where they are, but where they are entangled. So imagine this: you're lying still in your room, but some part of you, made of electrons and possibility, is still wrapped around something or someone else, an object, a memory, a star that blinked its last light before you were born. What matters is the connection, not the coordinates. And now your odd fact of the night. There's a theory called ERPA. It's not science fiction, it's a real hypothesis. Proposed by physicists Juan Maldacena and Leonard Susskind, it suggests that every entangled particle pair is linked by a tiny wormhole. Not one you can crawl through, but a mathematical bridge, a shortcut in the geometry of space-time itself. ER stands for Einstein-Rosen bridges, aka wormholes. EPR is the abbreviation for the entanglement thought experiment by Einstein, Podolsky, and Rosen. ER equals EPR means maybe all entanglement is actually tiny geometry. Invisible tunnels, built not for travel, but for connection. Now, nobody's sent a cat through a quantum wormhole just yet, but the idea alone shifts the ground beneath your feet, or under your particles. Because if space is emergent, if location is built from entanglement, then the most distant thing in the universe might also be right next to you, in the only way that matters. Don't worry if this is hard to imagine. That's part of the lullaby. Some things are meant to be felt more than solved. This isn't the place for certainty. It's the space where thoughts stretch and soften, like light through fog. And you might ask, how does this relate to anything real? Well, think about how you remember things. When you recall a moment, say, the smell of your grandmother's kitchen, it doesn't travel to you across time. It just is. Immediate, whole. The neurons light up and the past is suddenly present. No wires, no journey, just connection. Quantum mechanics is like that. It tells us that some things are simply bound, no travel needed. No middleman, just one continuous, wobbly, gorgeous yes. And yes, scientists still debate whether entanglement truly defies space, or whether it's just our interpretation of the math. But even in debate, something wonderful emerges, a willingness to question what we mean by real. So here's a closing thought for tonight. Maybe distance is a trick the universe plays on itself, a soft illusion, like a dream we haven't fully woken from. And maybe the people and places that feel far away never really left at all. You don't have to understand it. You just have to rest in the idea. There's a point in every dream where logic loosens, and things make just enough sense to keep floating. That's where you are now. Still, gently orbiting this quiet mystery. Because even in dreams, a question echoes. Is the quantum world complete? Tonight, we walk into the debate that made quantum mechanics feel like a puzzle with missing pieces, the one that Einstein, Podolsky, and Rosen placed squarely in the heart of physics, like a handwritten note. Something doesn't add up. They weren't conspiracy theorists. They were brilliant scientists who believed that nature, at its core, should be clear, predictable, local, real. So when quantum mechanics started describing particles as clouds of probability, Einstein was not amused. He preferred a universe where particles had identities solid, reliable, and not dependent on who's looking. In 1935, the trio published a now famous paper, usually just called EPR. It proposed a simple but devastating question. If quantum mechanics says two particles can be entangled and instantly affect each other at a distance, doesn't that mean either A, information travels faster than light, or B, particles don't have properties until we measure them? Both answers sounded wrong. So EPR offered a third option. Quantum mechanics is incomplete. That there must be something hidden, some deeper layer of reality, filled with variables we just hadn't discovered yet. Something that restored sanity. You know, sanity. that quaint 20th century idea that reality exists even when no one is looking. To support their point, EPR imagined two particles that interact, become entangled, and then fly apart. According to quantum theory, neither particle has a definite spin until one is measured. But if you can measure one and instantly know the other, then either information travels instantly or each particle always had a real value that quantum mechanics just didn't reveal. EPR chose the latter. They didn't want a spooky universe. They wanted a hidden one. But then along came a quiet Irish physicist named John Bell. He read the EPR paper decades later and thought, let's test it. Let's figure out, once and for all, if the world is hiding secrets or if quantum weirdness really is all there is. More on him in a minute. First, let's take a breather with your science fact for tonight. Particles can become entangled in such a way that neither one has a definite property, but the relationship between them is perfectly defined. It's like having two jigsaw puzzle pieces that don't yet have their individual shapes, but they still fit together perfectly when measured. The universe doesn't assign their forms in advance. It just ensures the pieces match. This is why the EPR paradox was so disturbing. It called into question not just the math, but the meaning of measurement. When you measure a quantum system, you don't just learn something about it. You help define what it is. Before measurement, it exists in a superposition, a mix of all possibilities. Only when you check do the probabilities collapse into reality. So EPR argued, surely this can't be the whole story. Surely reality exists independently of our poking. But quantum mechanics pushed back. And here's your odd fact of the night. A later extension of the EPR argument involved cheese. Yes, cheese. A thought experiment once asked whether it was possible to teleport the quantum flavor of a cheese molecule from one place to another using entanglement. The idea didn't pan out, but the metaphor stuck. What are we teleporting, if not the particle itself? Don't worry, we'll get to teleportation soon. For now, stay with the EPR puzzle. It's a question of faith, in a way. Do you believe the world has definite properties when no one's looking? That every particle, every quark, is a little soldier marching in line, even if we haven't spotted it yet? Or do you accept the unsettling alternative, that reality is fuzzy, floating, potential until your attention brings it into being? Physicists still argue about this. Some say quantum mechanics is a tool for prediction, not a map of reality. Others believe the weirdness reveals something deep, a fundamental truth about how the universe works, not just how it looks on paper. And yes, scientists still debate whether hidden variables could someday explain entanglement without resorting to faster-than-light influence. But so far, no hidden variables have passed the test. So here you are, centuries of thought humming quietly in your ears, wondering what it means to measure something. You measure the temperature of your room. You measure your heartbeat. You measure how far you've come in life, or how much you miss someone. But in the quantum world, measurement is creation. It's the act that brings possibility into form, a moment of birth disguised as discovery. And maybe that's what made EPR so emotional, not just for physicists, but for dreamers, because it feels like we're being asked to participate in the story, that until we look, the ending hasn't been chosen. Tonight, you're part of that story. Not an observer, but a quiet collaborator. The paradox isn't solved yet, but it hums. You've held the EPR paradox like a snow globe shaking gently, watching the flakes of doubt swirl around reality. But the next person to pick it up didn't just watch. He cracked it open. Enter John Bell, not a wizard, not a celebrity physicist, just a quiet mind who asked, what if we could test this? Because up until the 1962nd, the EPR paradox lived in the realm of thought experiments, cozy debates by fireplaces and blackboards. It made for good philosophy, but no one thought you could actually prove whether hidden variables existed. But Bell did, and what he uncovered was as elegant as it was explosive, a way to mathematically show whether entangled particles followed secret instructions or if their behavior was genuinely born out of quantum weirdness. This became known as Bell's inequality. Don't worry, we're not doing math. You're in bed. But imagine this. You're playing a quantum coin toss game with Lulu and Juno again. You flip their states using two distant detectors with settings chosen at random. Bell figured out that if the particles were pre-programmed, as Einstein hoped, then there was a strict limit to how correlated their outcomes could be. It's like setting up rules for a cosmic game show. If these particles are just hiding answers, then no matter how tricky the host gets, their scores should never go above X. But quantum mechanics? It routinely scores above that limit. Again and again, experiment after experiment, entangled particles blow past Bell's inequality. They don't behave like classical objects with hidden answers. They behave like actors in a play, where the script only appears when the spotlight hits the stage. And this is your science, fact of the night. Bell's theorem showed that no local hidden variable theory can explain quantum entanglement. In other words, if quantum mechanics is correct, then the universe is fundamentally non-local. Let that settle in, because non-local doesn't mean teleportation or instant messaging. It means connection without proximity, a tapestry where threads tug each other without touching. Bell's work didn't just challenge Einstein's skepticism, it made it testable. And once it was testable, the experiments followed. France, Switzerland, the Netherlands, even satellites. Each time, physicists tried to find a loophole. Maybe the detectors were talking. Maybe light had time to cheat. Maybe the particles had memory. But no matter how the tests were designed, the same result whispered back. Entanglement is real, and it doesn't care about our rules. Here's your odd fact of the night. Some researchers have used starlight from distant galaxies billions of years old to determine detector settings in quantum experiments. Why? To make sure no local signal, no Earth-based influence, could coordinate the results. It's called a cosmic Bell test. The results? Still spooky. So what did Bell do, really? He didn't explain away the weirdness. He proved that any universe hoping to behave normally couldn't produce the outcomes we observe. He cut the last rope, holding us to classical intuitions. And in doing so, he revealed something bigger. That the universe might be fundamentally random, not just chaotic but open. A place where cause and effect don't always ride the same elevator. This leads us to a question that's not in the textbook. What does this mean for you? Well, maybe you've felt like your life should follow rules. That A must lead to B. That people, choices, moments all have one logical path. But Bell's work reminds you that reality doesn't always tick like a clock. Sometimes, things are connected in ways that defy explanation. Sometimes, you can't trace the thread, you just feel the tug. And yes, scientists still debate whether Bell's theorem closes the door completely on hidden variables, or whether some exotic, non-local theories might still exist. But for now, the math stands, and it hums, softly, like a lullaby that doesn't rhyme but still makes you sleepy. So tonight, let's thank John Bell not for solving everything, but for making it real, for showing that entanglement isn't just a metaphor or a magical trick. It's physics. It's built into the bones of the universe. And you, made of those same particles, carry that mystery too. Somewhere in you, something is entangled with something else. And no one, not even Einstein, can say how far that connection reaches. The wind is softer now, if it's moving at all. Your body heavier, but your mind curiously light. That's the thing about entanglement. It doesn't rattle like thunder. It hums like fog. And tonight, you drift into the place where theory meets fingertips, the lab. Because everything we've floated through so far, EPR, Bell, Einstein's raised eyebrows, they were all maps drawn in chalk and ink. But now, the experiments begin. And suddenly, the ghost stories of physics come face to face with photodetectors, timing lasers, and very patient graduate students. You arrive quietly at a quantum optics lab. It doesn't look like a temple of mystery. There are tangled wires, humming machines, a whiteboard covered in equations someone forgot to erase, and right in the middle, a crystal. Not just any crystal, a non-linear one, the kind that, when struck by a high-energy laser, can split a single photon into two lower energy photons. A little quantum magic called spontaneous parametric down conversion. Sounds like a made-up Harry Potter spell, doesn't it? But this is real. When a photon enters the crystal, it's like a coin being sliced into two coordinated pieces, each new photon heading in a different direction, yet forever linked in polarization or momentum or some other entanglement trait. You've just created entanglement, not in thought, in light. Here's your science fact to hold like a warm cup. Entangled photons are routinely generated in labs all over the world, using simple components, lasers, crystals, and detectors. We've gone from theory to engineering, from spookiness to circuitry. And now, these photons need to be measured. That's where the real fun starts. Two detectors are set up, often in separate rooms or even buildings, sometimes kilometers apart. Each one gets a photon. The detectors are rigged to randomly choose what to measure, say, a photon's polarization at a certain angle. The goal? To check whether the results correlate more strongly than random chance allows. And they do, every time. The entanglement survives separation. The measurements agree far too perfectly for any classical theory to explain. And before you ask, yes, they've tried cheating. Over the years, physicists have hunted down every possible loophole. Maybe the detectors were slow. Maybe there was a hidden channel. Maybe the photons were reading minds. One by one, those loopholes were closed. And still, the results held. In 2015, the loophole-free Bell tests proved, as rigorously as we've ever seen in science, that no local hidden variable theory can explain what's going on. Let's pause for your odd fact of the night. In some tests, the measurement settings are chosen using light from distant stars. Imagine, a photon that left a galaxy 600 million years ago helps decide which angle a detector will use. Why? To prove that no Earth-based conspiracy could have arranged the outcome. Yes, quantum physics is petty like that. It doesn't just want to win, it wants to win cosmically. And while the experiments get more sophisticated, the mystery deepens. Every time entanglement is confirmed, it reinforces the idea that the universe isn't built like Lego bricks stacked and local. It's more like origami folded in on itself, where distance is deceptive and edges meet in secret. And what about you? Maybe you've had your own experiments, those quiet tests of trust, of instinct, of connection. You think of someone, and they call, you make a decision, and the world bends to accommodate it. Coincidence? Probably. But coincidence, in a quantum world, becomes harder to dismiss. And scientists? They still debate whether these tests fully prove non-locality, or whether some clever reinterpretation might rescue realism. But honestly, that debate is like arguing about shadows on a moonless night. The shape is there, the light just hasn't caught up yet. So next time you hear the word entanglement, don't picture a string, picture a rhythm, a shared beat, two dancers in different cities, stepping in time to music no one else hears. And in this moment, that dancer might be you. Not metaphorically, literally, because the particles in your body, electrons, quarks, gluons, they were born in stars, collided with photons, brushed against atoms from other bodies, other lives. Somewhere, entanglement threads still twitch. It's not magic, it's memory, physics written in relationships. So let your thoughts quiet. You've visited the lab, seen the detectors hum, the photons flicker. The weirdness isn't hiding anymore. It's blinking green, confirmed, verified, undeniable. And maybe, as you exhale and feel your chest rise and fall, you'll wonder if somewhere a photon responds, not because you caused it, but because you and it were never quite apart. You've seen entanglement tested in labs, confirmed across rooftops and starlit skies, but how do you actually create it? Like, where do you get a pair of particles so spiritually codependent they finish each other's quantum sentences? Tonight, you drift deeper not into equations, but into the art of the setup. Because while entanglement sounds like something that happens spontaneously in the enchanted forest of the subatomic world, it actually requires craftsmanship, timing, patience, and of course, lasers. Let's return to the crystal, the magical block you met earlier, capable of slicing one photon into two. The process is called spontaneous parametric down conversion, and while it sounds like a sleep setting on your phone, it's actually how many entangled photons are born. Here's how it works. A strong laser beam enters the crystal. Most photons pass through untouched, but once in a while, a single photon will split into two lower energy photons. These two are emitted at equal but opposite angles, with their quantum properties like polarization linked forever. Voila, entanglement, gently handcrafted. But don't let the magic fool you. It's a fragile thing. Imagine two figure skaters twirling in perfect synchronicity. Now imagine trying to keep them in step while the entire ice rink is vibrating, the lights keep flickering, and an intern keeps opening the door. That's how delicate these particles are. Any stray interaction, dust, heat, vibration can cause decoherence, which is like the entangled state falling apart from being watched too hard. Entanglement hates attention. It thrives in the shadows, in silence, in solitude. Even a single bounce off a nearby atom can ruin it. So the lab becomes a sanctuary. Vibration-isolated tables, cryogenically cooled chambers, detectors timed to the nanosecond. Creating entanglement is not just an experiment, it's a ceremony. And here's your science fact for tonight. Quantum entanglement has been created not only in photons, but in ions, superconducting circuits, atomic ensembles, even tiny mechanical oscillators. It's not just a light trick, it's a universal principle, which means entanglement isn't picky. It just demands respect. Now, imagine trying to scale this up. Not 2 photons, but dozens, hundreds, trying to entangle a whole system, not just a pair, but a family. Suddenly, you're not just crafting a magic trick. You're building the foundation for quantum computing, quantum networks, and even quantum teleportation, but don't float there just yet. We'll get there soon, like a bedtime treat. First, let's enjoy the weirdness of entanglement swapping. Yes, swapping, because apparently, entanglement is social. Here's your odd fact of the night. You can entangle 2 particles that have never interacted by entangling each of them with a third particle and then cleverly measuring the middle ones in just the right way. It's like introducing 2 strangers by destroying their mutual friends. And it works. That's the wild part. The 2 end particles, which never shared a photon, now behave as if they did. Scientists call this entanglement swapping, and it's key to building large quantum systems, like setting up a game of telephone where nobody knows who's talking to whom, but the message still arrives perfectly. So, if you're keeping track, you can create entangled particles. You can protect them, kind of. You can even entangle things after the fact, which should not be allowed. But quantum doesn't care about your feelings. And yet, for all this power, entanglement remains shy. It vanishes the moment someone stares too hard. It refuses to be used as a telephone. It requires us to set the scene, whisper gently, and then step back. Maybe that's why it feels familiar. We've all known connections that work like that. Friendships that dissolve when forced. Relationships that spark in silence but fade under scrutiny. Sometimes, things only work when you don't try to own them. And yes, scientists still debate how scalable entanglement really is, and whether large entangled systems can survive long enough to be useful outside pristine labs. But the efforts continue, carefully, lovingly. So tonight, as you float toward the edges of sleep, imagine yourself in that lab. The lights are dim, the lasers pulse like sleepy fireflies. You sit at the edge of the table, watching 2 particles that were once part of the same photon drift in opposite directions, still whispering to each other in ways no cable could carry. No drama, no noise, just presence. That's entanglement. It doesn't shout, it listens. And you? You don't need to do anything. Just keep breathing. You're already part of the conversation. Now that you've helped birth entanglement delicate as gossamer, you also have to face its natural enemy. Not a villain in a cape. Not even something trying to destroy it. No, entanglement's undoing is far more mundane. It's called decoherence, and it happens the moment the world gets involved. Imagine you've just written a secret, on a foggy window. It's private, meaningful, and perfectly balanced between presence and invisibility. Then someone turns on the fan. That's decoherence. In the quantum world, maintaining entanglement is like keeping a dream from fading at sunrise. Anything that brushes against your entangled particles, heat, sound, air molecules, a curious glance can collapse their shared state. Why? Because quantum systems don't just exist. They exist in relation to other systems. And when something in the environment interacts with them even slightly, it's as if the particles are forced to pick a side. No more, maybe, just is. This is what physicists call environmental measurement. The world peeks in, and suddenly, the quantum spell breaks. You can think of decoherence as nature's way of forcing quantum systems to play by classical rules. Here's your science fact to sip like warm tea. Decoherence happens incredibly fast, often in femtoseconds. That's a millionth of a billionth of a second. For quantum computers and experiments, preventing decoherence is like trying to keep a snowflake intact inside a hairdryer. That's why labs go to such extremes. Cooling systems to near absolute zero, shielding from electromagnetic interference, even suspending particles in vacuum chambers so they don't bump into an errant gas molecule. Because in the quantum world, bumping is betrayal. Even stray light can cause decoherence. If a photon lands on your qubit, your entangled buddy, it's game over. The entanglement collapses. The particle chooses a side. The perfect ambiguity vanishes, and you're left with something normal, predictable, boring. You're back in the land of clocks and toasters. And this is where the quantum gets personal, because haven't we all experienced decoherence of another kind? Those moments where magic gives way to noise, where the connection you felt with someone dissolves after one awkward conversation, where your creative spark dims the second you try to explain it to someone who doesn't get it. We don't call it decoherence in everyday life, but it's that same fragile state, beautiful while unmeasured, ruined the moment it's forced to collapse. And now, your odd fact of the night, there's ongoing research into controlling decoherence instead of just fighting it. Some scientists are exploring how environmental noise can be harnessed, used to guide quantum systems without fully collapsing them. It's called dynamical decoupling. And yes, it sounds like quantum yoga. So it's not all doom and collapse. Decoherence is part of the story, not the end of it. In fact, decoherence is likely the reason you feel like a coherent person. Think about it. If your atoms were constantly in quantum superpositions, you couldn't walk, talk, or text. You'd be a fog of possibilities, unable to form a single thought. But because your particles interact constantly with each other and with their surroundings, your body decoheres into something stable, something consistent, something you. There's beauty in that too. Stability born from complexity. Reality as a byproduct of constant conversation between parts. And yet scientists still debate where the line is between decoherence and true measurement. Is there a threshold? A final collapse? Or does it happen gradually, like morning light soaking through curtains? We don't know. But here's a soft thought to fall asleep with. Maybe life is a balance between entanglement and decoherence, between mystery and definition, between keeping things in superposition and letting them collapse into something solid. Some things you hold loosely like dreams, memories, hope. Others you let collapse like decisions, moments, love turned real. Entanglement shows you what's possible. Decoherence teaches you what remains. And right now, as the world quiets and your mind drifts inward, you don't have to hold anything. Not an answer, not a concept, not even your breath. Just be the system, floating, slightly entangled, slightly observed, and completely at rest. You've floated through the ether of connection, witnessed the heartbreak of decoherence, and now something extraordinary appears just beyond the horizon of understanding. Teleportation. Yes, really. Quantum teleportation is not the kind that beams your body from your bed to a beach in Tahiti, though we'd all appreciate that service. No, this is subtler, stranger, It doesn't move matter, it moves information. It doesn't transport particles, it recreates them somewhere else. Let's ease into this. Say you have a particle, let's name it Kiki. She has a quantum state, a sort of delicate identity, her spin, her orientation, her mood, if you like. But you can't just copy her. Quantum mechanics forbids it. This is known as the no-cloning theorem. So you can't Xerox Kiki. You also can't simply measure her and reconstruct her elsewhere because measuring collapses the state. It's like trying to photograph a soap bubble by popping it. So how do you move her? Well, you cheat elegantly. You start by preparing an entangled pair of particles. Let's call them Lulu and Juno, your usual dream team. Lulu stays with you. Juno is sent far away, say, to your friend floating on a cloud. Now, you bring Kiki into the room with Lulu. You perform a very specific quantum operation, a Bell state measurement on Kiki and Lulu together. This doesn't tell you what Kiki was. It tells you how Kiki and Lulu compare in a way that's full of entangled possibility. And the result? Kiki's exact quantum state disappears from your location and reappears in Juno. Not a copy. A perfect reconstruction, as if Juno becomes Kiki. You haven't moved the particle. You've moved its essence. Its being. Kiki is gone from you and reborn somewhere else. You've just teleported a quantum state. Take a breath here. It's okay if this sounds like science fiction, but it's real. This isn't a metaphor. This is a verified process. It's been done with photons, ions, even with states encoded in light pulses and atoms. Not across galaxies yet, but across labs, fiber optic cables, and, yes, even satellites. And here's your science fact of the night. In 1997, physicists in Innsbruck and Rome independently demonstrated the first successful quantum teleportation of a photon's state. Since then, researchers have teleported quantum states across dozens of kilometers of fiber and between Earth and space. Teleportation isn't a dream, it's a protocol. But let's address the elephant on the teleportation pad. This isn't faster than light communication. You still need a classical signal, a regular message sent at light speed to complete the process. That's because the result of your Bell state measurement doesn't determine the final state. It only tells your partner how to adjust Juno to recreate Kiki. In other words, quantum teleportation requires both entanglement and regular communication. It's spooky, but still plays fair with Einstein's speed limit. And here's your odd fact of the night. There's a serious international effort to use quantum teleportation to build the backbone of a future quantum internet. Imagine a network where information is teleported, not copied, secure, instant, and unhackable by classical means. But what does this have to do with you? Well, let's gently stretch the metaphor. Maybe you've known a moment when part of you was elsewhere. Not just emotionally, but intellectually, spiritually. A word spoken across a distance that reached you like it was meant only for you, a glance that said more than a letter. Teleportation isn't only about moving data, it's about trust. Two ends of the line must be entangled. The setup must be precise. You must be willing to give something up in one place, for it to exist again in another. There's no room for greed in teleportation. You lose what you send, and maybe that's a rule life shares. To send something beautiful, truth, love, clarity, you must let it go. You can't keep it and share it. You must give it away, trust it'll arrive whole. And yes, scientists still debate how scalable quantum teleportation can become, and whether it could ever be used to transfer states of complex systems like molecules or dreamily brains. But tonight, that debate isn't your burden. Tonight, you're the quiet observer, watching Kiki's state disappear into math and lasers and reappear light years or meters away, like a whisper carried on silence. You don't need to calculate the matrix. Just feel it, that sometimes connection isn't about proximity. Sometimes it's about preparation, surrender, and faith that what leaves you might live on exactly as it was meant to be in someone else's open hands. You've just watched a quantum state vanish from one place and reappear somewhere else, the pulse of identity flickering through the vacuum, riding on threads no one can see. But even now, a question glimmers beneath your closed eyelids, like a half-remembered riddle. If particles can be entangled, and states can be teleported, why can't we use this to send messages faster than light? You're not the first to ask. It seems obvious entangled particles respond to each other instantly. So if Lulu is in Paris and Juno is on Mars, and you measure Lulu, surely you could signal to Juno by choosing what to do with Lulu, right? Nope, quantum mechanics says, not so fast, sleepyhead. This is where we meet the no-signaling theorem. It's like the quiet librarian of quantum physics whispering from behind the stacks. You may observe spooky correlations, but you shall not transmit meaningful information through them. Let's slow it down. When you measure an entangled particle, yes, the other one's state becomes instantly determined, but you don't get to choose the outcome. It's random. Truly, deeply, frustratingly random. So even though Juno's particle is instantly affected by what happens to Lulu, no observer can use that change to send a message. It's like opening a pair of magically synchronized fortune cookies. You both get the same prediction, but neither of you can decide what that prediction will be. You can't signal help or buy Dogecoin. All you get is quantum poetry written by the universe, unread until both of you compare notes. And that comparison? It requires a regular, classical message. An email, a laser pulse, a text, something that moves no faster than light. So teleportation doesn't break Einstein's rules. It skirts the edge. It winks at them, but it never steps over. Here's your science fact of the night. The no-signaling theorem is mathematically derived from the basic rules of quantum mechanics. It guarantees that entanglement cannot be used to transmit information faster than light, preserving causality and keeping paradoxes at bay. So yes, entangled particles are connected, but they're not walkie-talkies. Now, before you sigh and roll over disappointed, let's flip the perspective. There's a kind of beauty in this constraint, because imagine if entanglement did allow faster-than-light messaging. You could communicate instantly across the universe. But at what cost? Time would become tangled, cause and effect would unravel. You could receive a message before it was sent. Your grandma could tweet you from the future. Cats might evolve email. In short, chaos. The no-signaling rule preserves order. It keeps the world narratable. And yet, even with this rule in place, quantum systems still exhibit something called non-locality, that eerie coordination across distance. You can't use it to send messages, but it's there, as if the particles are whispering behind glass you can't tap on. This is where things get philosophical, because haven't you felt something like this before? The kind of connection that isn't about communication, but about alignment. You think of someone, and they're already thinking of you. You feel something shift, far away for no logical reason, no message passed, no cause traced, just a shared state. Coincidence? Always. But remember, in quantum mechanics, even the impossible is just the edge of the known. And here's your odd fact of the night. Some scientists have proposed superdeterminism as a possible loophole, suggesting that everything, including your measurement choices, was already determined by hidden variables. It would explain the perfect correlations without needing spooky action, but at the cost of free will. Yes, you heard that right. To remove the weirdness of quantum entanglement, you'd have to abandon the idea that you choose anything, that even now, lying there, deciding to breathe deeper, that too would be scripted. Most physicists politely pass on that idea. So the no-signaling rule stays, and with it, the tension. Entanglement connects things across space, but without control. Teleportation moves information, but only with classical cooperation. In other words, you can't send love, but you can send the readiness to receive it. That might be the best kind of connection. It's not about control, it's about preparation, about building the entangled link and waiting patiently for the signal. And yes, scientists still debate whether the no-signaling theorem rules out all forms of quantum communication, or whether clever tricks might someday exploit the edge of what's possible. But so far, physics remains stubbornly silent on the faster-than-light front. And perhaps that's okay, because not everything needs to be said. Not every link needs to be loud. Some things, some feelings, some moments are entangled quietly, never measured, never used, only known. So tonight, drift deeper into that silence, where cause and effect loosen their grip, where messages arrive in stillness and meaning flows without motion. You've sat quietly with a no signaling rule watched, it draw an invisible line between connection and communication. But now the rules stretch again, and something spectacular begins. You're about to teleport a quantum state across the lab. This isn't a metaphor. You're lying there, blanket tucked, eyes almost closed, and yet you're also inside a sleek glass chamber where photons dance and fiber optic cables snake like sleeping vines. On one side of the room, Alice. On the other, Bob. Classic names, timeless confusion. Bob wants to receive a quantum state. Alice has the state of photon named Kiki, spinning in a precise orientation, but she can't send it directly. Not if she wants to preserve its full quantum weirdness. So they agree on the plan. Quantum teleportation. Step 1. Entanglement. Alice and Bob each get one particle from an entangled pair, Lulu and Juno. Bob tucks Juno into a detector across the lab. Alice holds onto Lulu and places Kiki, the unknown state, beside her. Then, she performs a Bell state measurement on Lulu and Kiki. This doesn't give her any direct knowledge of Kiki's state. Instead, it collapses the system into one of 4 possible outcomes, each corresponding to a different way that Juno, at Bob's side, must be rotated to become Kiki. Now, crucially, Alice sends Bob a classical message. Hey! Outcome number 3. Rotate Juno 180 degrees around the x-axis. Bob obeys. And just like that, Kiki's state has disappeared from Alice's location and reappeared in Bob's. Not a clone, not a peak. The exact state reconstructed. Teleportation complete. Here's your science fact to rest your head on. In 2004, researchers at the University of Vienna performed quantum teleportation over a distance of 600 meters using optical fiber in the city's sewer system. The particles were literally entangled underground, like some secret science opera humming beneath everyday feet. So yes, it's real. Not theoretical, not sci-fi. Teleportation has walked through the world wearing lab coats and fiber cables. And it gets weirder. In 2017, scientists in China used a satellite Meishes to teleport a quantum state from the ground to orbit, more than 500 kilometers away. The photon's quantum information leapt from Earth to space, like it was playing hopscotch on starlight. Teleportation, above the clouds. But again, nothing material moved. No atoms jumped. No particles whooshed through the atmosphere. It's like Kiki's soul was transferred, not her body. And here's your odd fact of the night. Quantum teleportation doesn't violate the no-cloning theorem because the original state is destroyed during the process. In order for Juno to become Kiki, Kiki must vanish. You can't make copies. You can only let go. Which brings us back to you. Have you ever had to let something go in order for it to live somewhere else? A thought, a feeling, a version of yourself? Teleportation isn't just science. It's a metaphor for transformation. You don't get to hold on and move forward. You don't get to keep the original and create the new. You must release what you are, so that it may become something somewhere else. And what about the person on the other side? They can't just guess what to do. They need the classical message, the quiet email, the whispered instruction. Without it, Juno remains a flicker of possibilities. So even in quantum teleportation, perhaps, especially in quantum teleportation, trust is required. 2 systems must prepare. One must act, the other must wait. And when the message arrives, the state completes. Sound familiar? Relationships work the same way. You build the connection, invisible but strong. Then comes the leap, the moment when something unspoken moves between you. And if the line holds, if the instructions are clear, a new self takes form. And yes, scientists still debate whether teleportation could one day scale beyond single qubits, or extend to molecules, or ever reach something resembling memory or thought. But for now, it's enough to know. Information, identity, essence, these can move without motion. That alone is a lullaby worth singing. So as you drift deeper, feel yourself as both Alice and Bob, the sender and the receiver, the one who holds and the one who waits. And in between, a field of entanglement, a message not yet sent, a state not yet born. Let go. Allow something unknown to arrive. You've teleported a quantum state across a room, watched it shimmer into existence like a message stitched into moonlight. But what happens when you want to go farther? Like, really far. Tonight, you're gliding past the edge of the lab into fiber cables stretched over city streets, lasers beaming through mountaintop skies, and the first sketches of what may someday become the quantum internet. But to get there, you need help, because quantum entanglement, as magical as it is, doesn't travel well. Remember decoherence? That delicate villain made of heat and noise? It waits around every corner, especially when you're trying to keep entangled particles together over long distances. You might start with a pair, but by the time they travel even a few kilometers, the link has usually collapsed, snapped, like a soap bubble touched by wind. So how do you stretch entanglement across continents? You cheat, again. But this time, you cheat with quantum repeaters. Think of them like enchanted lighthouses stationed along a dark shoreline, each one receiving a weakened signal and restoring it without collapsing it. In classical communication, a repeater just amplifies the message. But in quantum communication, you can't copy or amplify a qubit directly, remember, no cloning. So what do repeaters do? They use entanglement swapping. Let's break it down gently. You entangle particle A with particle B at one repeater station. Then you entangle particle C with particle D at the next. Now, you perform a clever measurement called a Bell state measurement on B and C, the middle pair. Surprisingly, this links A and D. Even though A and D never touched, never met, never shared a wave function, they're now entangled. It's like arranging a marriage between two people by marrying off their mutual cousins first. Quantum matchmaking. And here's your science fact. Quantum repeaters have been demonstrated in principle, and early prototypes exist. The challenge is in building them robustly, keeping the entangled states intact across noisy, imperfect environments. But the dream is alive, and glowing faintly on the horizon. A quantum internet. Imagine. Messages teleported, not transmitted. Security guaranteed, not by passwords, but by physics. A communication network so deeply encrypted that even the universe itself can't eavesdrop. Because here's the kicker. Any attempt to intercept an entangled message collapses it. There's no hiding, no hacking. If someone tries to listen in, the entangled state breaks. And you know immediately, it's the ultimate tattletale. This is the promise of quantum key distribution, the backbone of quantum encryption, already in use, already tested between satellites and ground stations. The future doesn't arrive with a trumpet. It lands on your rooftop with a photon. Here's your odd fact of the night. In 2020, scientists successfully entangled particles across more than 1,000 kilometers using the Mischius satellite. It's the longest distance quantum entanglement ever recorded. From mountaintop observatories in China to orbit and back again, spooky action took a long walk. So where does that leave you? In the quiet hum of a coming age, an internet built not on wires, but on wonder. A system where what matters is not what you send, but how you prepare. Where particles shake hands across continents, not with noise, but with silence. And yes, scientists still debate how scalable this network can be, whether quantum repeaters can maintain coherence long enough to stretch between cities, countries, even planets. But the first nodes are blinking on. So tonight, imagine your thoughts as particles. Tiny, entangled, glowing messages, drifting gently across the world. They don't arrive by force. They don't shout. They whisper, perfectly matched to the one ready to hear them. Maybe one of those nodes is a person. Maybe it's a place. Maybe it's a part of you you left behind long ago and are only now reconnecting with. Let it come. The network is building itself. No passwords. No noise. Just trust. You're no longer in the lab. You've left the fiber optics and vacuum chambers far below. Now you're floating somewhere above the Earth, softly orbiting with a Chinese satellite named Mycius, cradling a pair of entangled photons like lanterns in space. This isn't science fiction. This is the first real experiment in space-based quantum entanglement. Launched in 2016, Mycius was the world's first quantum science satellite. Its mission? To test whether entanglement could survive a journey through the noisy, chaotic, unpredictable emptiness between Earth and orbit. You'd think that would be easy. After all, space is empty, right? Not quite. Photons sent from orbit to ground must pass through the atmosphere where they scatter, bend, and face decoherence from every gust of temperature or wisp of cloud. Add in turbulence, timing, and the fact that both the satellite and Earth stations are moving, and suddenly this starts sounding impossible. And yet, they did it. In 2017, scientists successfully entangled photons between ground stations in China more than 1,200 kilometers apart, using Mycius as the middleman. The entanglement was preserved. The measurements matched. Spooky action survived the stars. That's your science fact of the night. It was one of the most delicate experiments ever done, not just for the precision, but for what it meant. Because entanglement, once a ghost story whispered by Einstein, was now orbiting the planet. Let that settle. Your childhood toy, those cans connected by string, just got replaced by a beam of light shooting from a mountain to a spacecraft. And what does it carry? Not words, not particles, but shared possibility. The two photons never touch, never speak, but what happens to one still shapes the other. That's not just physics. That's poetry with coordinates. And here's your odd fact of the night. To protect the entangled photons during transmission, scientists used ultra-narrow filters, sub-nanosecond timing, and precise tracking systems that kept laser beams aligned between satellite and telescope within a margin of just a few microradians. That's like aiming a flashlight from orbit and hitting a coin on Earth. And they pulled it off. Now, you might be asking, why go to space? Isn't that a bit dramatic? Actually, no. Space is the best place for quantum communication. On Earth, entanglement loses strength over distance. Fiber optic cables absorb light, noise builds, errors creep in. But in space, photons travel mostly in a vacuum. No cables, no friction, just darkness, waiting. Which makes Mycius the first node in what could become a global quantum network, satellites linking cities, continents, and perhaps, someday, lunar colonies. But let's float back to you. There's something tender about this whole setup. One particle on Earth, one in orbit, both born from the same beam, both drifting through different environments, but still entangled, still sharing a quiet, invisible thread. You've known that feeling. Think about the people you've grown apart from. Maybe distance, time, life, all of it has pushed you to opposite corners of the world. But still, something flickers, some thread hums. You think of them and they feel it. Not provable, not measurable, but real. Entanglement in space reminds us that connection doesn't fade with distance. It just becomes harder to detect, more subtle. It needs the right tools, the right timing, the right openness. And yes, scientists still debate how best to build a fully space-based quantum communication system. Issues of scale, cost, synchronization, it's all a work in progress. But the first step has been taken by a satellite gliding above your head, by a photon dancing through Earth's haze, whispering to its twin 1,000 kilometers away. You don't need to understand every equation, just know this. Some part of you may still be entangled with a moment you thought you lost, with a person who changed you, with a dream that burned brightly, then faded. It's not gone. It's orbiting, silently, waiting for the right conditions, waiting for you to look up and say, I remember. So rest now. The satellite is still overhead. The photons are still flying. And the universe, quietly, is still whispering across the dark. You're still drifting, quietly tethered to that distant satellite, the hum of entanglement like a lullaby stretched across space. And now, the question shifts. If two particles are connected across distance, what do they experience? What does entanglement feel like from the inside? It's easy to think of the photon on your windowsill and the one in orbit as two separate things. After all, they've traveled far, been touched by different forces, scattered through different skies. But if they are truly entangled, then in the language of quantum mechanics, they don't really have independent identities. Not entirely. They form one combined system, one mathematical wave function that just happens to be smeared out across space. When we measure one, we're not looking at a separate object. We're revealing a property of the whole system. And that's the quiet wonder hiding beneath the equations. Entangled particles don't see each other as distant, not in any way that matters to them. From the inside, there is no gap, no waiting, no in-between. It's only from our outside perspective, bound by light speed and clocks, that the strangeness appears. To the particles, it's just now. That might be the most dreamlike part of all, that even across space, what's entangled stays whole. So, when you measure your particle, and the result is up, and your partner's is instantly down, it's not that yours made the decision first, it's that neither was ever separate. They weren't choosing independently. They were revealing what was always true together. And here's your science fact to cradle as you drift. Entangled systems cannot be described just by adding up the descriptions of their parts. They require a single equation that treats them as a unified whole. This is called non-separability, and it's the heart of what makes entanglement different from any ordinary correlation. You've seen correlations before: smoke and fire, thunder and lightning. But entanglement is more intimate. It's not cause and effect. It's not signal and response. It's simultaneous identity. You change one side, and the whole shifts, not like pulling a rope, but like moving one end of a shadow. And here's an odd, beautiful fact of the night. In some interpretations of quantum mechanics, like relational quantum theory, the idea of objective properties vanishes entirely. There is no particle with a definite spin out there. Reality is made only of relationships, what one system observes about another. Nothing exists in isolation. Everything is seen into being, which leads us here to something human. Maybe you felt invisible until someone looked at you a certain way really looked. Not as a role or a label, but as a whole person. In that moment, something collapsed. Not your dignity, but your uncertainty. You became real in their gaze. That's what entanglement reminds us of. The importance of observation, not to invade or measure, but to connect. When we're truly entangled with someone or something, we don't just influence them. We define them, and they define us, even from far away. And yes, scientists still debate what really happens inside entangled systems. Some claim that nothing changes at all until both results are recorded. Others believe the wave function itself is real, and the connection is truly instantaneous. The debate sways like a pendulum between mathematical modesty and philosophical boldness. But wherever the truth lands, one thing is certain: the entangled don't measure each other, they complete each other. So, maybe the same is true for you. Maybe some part of you is still bound to a version of yourself that existed before things changed, before you let go of a dream, or took a different path, or said goodbye too early. Maybe that part of you still flickers in perfect alignment, waiting for the right moment to be observed again. Don't worry, there's no rush. In quantum terms, it's already there. Tonight, there's no need to collapse any state. Let the wave function spread. Let the possibilities remain tangled. You are whole not despite the distance between your thoughts, but because of it. Close your eyes gently. You don't have to see the other half to know it's there. The night deepens, and the rhythm of your breath softens into something slower, something looser. You've come far from crystals and lasers to satellites and dreams, and now you're standing before one of the strangest metaphors ever wrapped in mathematics: the cat that is both alive and dead. Yes, Schrödinger's cat. It started as a joke, or more precisely, a protest. In 1935, the same year Einstein and his friends dropped the EPR paradox into the world, Austrian physicist Erwin Schrödinger offered a bizarre thought experiment to highlight just how absurd quantum mechanics seemed when applied to real objects. If quantum particles could exist in superpositions being in multiple states at once, what would happen if you scaled that weirdness up? He imagined a cat, sealed inside a box with a radioactive atom, a Geiger counter, a vial of poison, and a triggering mechanism. If the atom decayed, the detector would trip, breaking the vial, releasing the poison, and, well, you know. If not, the cat lived. But here's the twist. Quantum mechanics said the atom existed in both decayed and undecayed states until measured. So the cat, by extension, was both alive and dead until someone opened the box. It wasn't meant to be taken literally. Schrödinger didn't hate cats. He hated how quantum mechanics seemed to blur the boundary between the subatomic and the ordinary, and yet his feline paradox became iconic, a sleepy, whiskered symbol of quantum strangeness. Here's your science fact to cradle like a curled-up kitten. The cat is not just a metaphor. In recent years, physicists have created actual macroscopic systems using superconducting circuits, vibrating membranes, and clouds of atoms that exhibit quantum superposition, not cats. But not just electrons either. The border between quantum and classical is thinner than we once believed. But what does this have to do with entanglement? Everything. Because Schrödinger's cat isn't just a paradox about measurement, it's an entangled system. The fate of the cat is entangled with the state of the atom. Until the system is observed, their outcomes are bound together, one undecided, the other undefined. And once you look, the wave function collapses. The possibilities split. You don't see both outcomes. You see one. The cat meows, or it doesn't. But what if we ask the question differently? What if the cat isn't waiting to be observed, but observing you? In some interpretations of quantum theory, especially the ones that make you squint before bed, consciousness plays a role in the collapse of the wave function. That without a conscious observer, the universe remains suspended in shimmering uncertainty. It's controversial, to say the least. Most physicists avoid tying their equations to minds, but the idea lingers like a scent. What if the act of noticing is more powerful than we think? Here's your odd fact of the night. In experiments using what's called a quantum eraser, scientists have shown that decisions made after a particle is detected can seemingly influence whether it behaved like a particle or a wave in the past, as if causality itself was optional. And suddenly, Schrödinger's cat feels a little less like a joke and more like an invitation, a whisper that the world is not fixed, that possibilities stretch further than the walls of a box. So how does this land inside your quiet night? Perhaps you've kept your own versions of the cat-boxed moments you've never dared to open. What if I had stayed? What if I had said yes? What if I had taken the other road? These are not regrets. They are entangled futures, still alive somewhere in the folds of your memory. And maybe that's the secret. You can't know them all. You can't live every version. You must open the box eventually. You must choose. But for now, as your body sinks deeper into the mattress, you're allowed to hold the mystery. Let the cat sleep. Let the atom hum. Let the system remain beautifully uncertain. And yes, scientists still debate where the line lies between quantum possibility and classical reality. Some say it's a matter of scale, others say it's about interaction. A few still whisper that it has something to do with you. So tonight, stay just a little unmeasured. Let your thoughts exist in superposition, resting between sleep and waking, between knowing and wondering, not alive or dead, not right or wrong, just gently entangled with what might be. You don't have to open the box. Not yet. You just have to close your eyes. You're weightless now, no longer bound by boxes or paradoxes. The cat sleeps undisturbed, and the lab has faded behind you. Ahead, something new glimmers, something practical, yet steeped in quiet wonder, a lock that breaks if anyone tries to pick it. Tonight, you drift into the realm of quantum cryptography. It's not just a clever buzzword. This is where entanglement becomes useful in the most poetic way possible, by making secrets impossible to steal without revealing the theft. Let's begin with a simple image. Two people, Alice and Bob, again, wish to share a secret, a code, a password, but they're worried. Maybe someone is listening. Maybe someone, Eve, the eternal eavesdropper, is lurking in the background. In the classical world, you solve this with encryption scrambling the message with a key. But keys can be intercepted. Computers can be fooled. Patterns can be cracked. What you need is a method that not only hides the key, but makes its theft impossible without detection. And that's exactly what quantum cryptography offers. The most famous method is called quantum key distribution, or QKD. It uses individual photons, each with a randomly chosen polarization, to create a string of bits shared between Alice and Bob. These photons are delicate, like soap bubbles in moonlight. Any attempt to intercept them, even to glance at them, changes their state. That's the quantum rule. Measurement disturbs. So if Eve tries to listen in, her interference alters the data. It introduces errors, noise, static. Alice and Bob compare a portion of their key, and if the error rate is too high, they know someone was watching. No need to guess, no need to trace. The message protects itself. Here's your science fact to tuck beneath your pillow. In 2007, the Swiss government used quantum cryptography to secure their election data. In 2010, China built a 2,000-kilometer quantum communication line between Beijing and Shanghai. Quantum encryption isn't theory anymore, it's infrastructure. But the beauty lies deeper, because this isn't just about safety, it's about trust. Not trust in people or passwords, but in physics, in the fabric of the universe. You're using the fragile nature of quantum systems as a shield. You're saying, this is so delicate that no one can touch it without leaving a fingerprint. And maybe, just maybe, that feels familiar. Because haven't you had truths like that? Thoughts or memories so fragile, so shimmering with significance, that speaking them changed them. People you trusted with a secret, only to feel it bend under their gaze. Sometimes, the most powerful form of security isn't armor, it's transparency. That's what quantum encryption teaches us. And here's your odd fact of the night. Some protocols don't even require transmitting entangled particles. They use single photon states in specific bases, called the BB84 protocol, invented in 1984 by Bennett and Brassard. It's simpler than full entanglement, but still purely quantum, still perfectly untouchable. And yet scientists still debate how scalable and practical quantum cryptography will be. Can it work globally? Can it survive real-world interference? Can it coexist with our clumsy, classical networks? But those are questions for engineers. Tonight, you're floating with the idea that you can create a message no one can steal. That truth can exist in a state where interference reveals itself. That some things, your quiet hopes, your inner voice, your unspoken knowing, are encoded not to be hidden, but to be honored. Quantum cryptography doesn't keep people out. It just ensures that if they enter, you'll know. So rest in that certainty. Not everything has to be locked in a vault. Some things are safe simply because of how they exist. Like love that can't be faked. Like light that changes when watched. Like you entangled, encrypted, still softly glowing in the dark. The deeper you drift, the more it feels like quantum mechanics isn't confined to labs and satellites, it's everywhere, quietly pulsing beneath the surface of things. And tonight, as the room fades into hush and your body forgets to worry, we ask a gentle question. Could entanglement be hiding in nature itself? Not in wires or crystals or high-tech gadgets, but in wings, in feathers, in brains. Let's start with the birds. There's a particular kind of bird, the European robin, that migrates with uncanny precision, even in total darkness, even through magnetic storms. For years, scientists were baffled. How could these tiny creatures know where north was, when clouds blocked the sun and Earth's magnetic field offered no visual cue? The answer, strangely enough, may lie in quantum entanglement. Inside the robin's eye, researchers believe, is a special protein cryptochrome that, when struck by light, forms pairs of entangled electrons. These electron pairs, affected by Earth's magnetic field, influence the bird's vision, allowing it to literally see the magnetic direction, like a built-in compass layered over the world. If true, it would mean that birds are navigating using entanglement. Let that flutter inside you. The same principle used in our most advanced physics labs might already be at work in feathers. And here's your science fact to tuck beside your heartbeat. Studies have shown that cryptochrome proteins in birds, and even in some humans, can form radical pairs whose spin states are sensitive to magnetic fields. This process, while not direct proof of entanglement, behaves in a way that suggests it, enough that the theory holds flight. But what if the mystery doesn't stop with birds? What if entanglement touches the mind? Some researchers have explored the possibility that the brain may maintain entangled particles long enough to influence cognition, not thoughts exactly, but processes, coherence, timing, awareness. Tiny proteins called microtubules, woven through your neurons like scaffolding, have been proposed as potential quantum processors. They're incredibly ordered, insulated from noise, and small enough to support quantum effects. It's a controversial theory, whispered more than shouted, but it hums with possibility, because if true, it would mean that consciousness isn't just an emergent property of chemical signals and electric pulses. It might also involve quantum coherence, not just noise but music, not just matter but entanglement. And here's your odd fact of the night. Some plants use quantum coherence to optimize photosynthesis. When sunlight hits a leaf, the energy is passed through a network of molecules in a way that seems to explore all paths at once, choosing the most efficient route with almost no loss. A kind of natural quantum algorithm running on chlorophyll. So birds may fly with entanglement, brains may think with it, leaves may harvest light with it, and suddenly the world doesn't feel like a machine anymore. It feels like a field woven, shimmering, aware, where particles don't just bounce and collide, but communicate in ways deeper than cause and effect. And yes, scientists still debate whether these effects are truly quantum in nature, or whether classical systems can explain the patterns. The experiments are difficult, the systems complex. The boundary between noise and coherence is razor thin. But even the debate is beautiful, because it reminds us that the line between physics and life is not as sharp as we thought. Maybe you've known that all along, the feeling that your choices ripple further than they should, the sense that your memories stretch beyond your body, the quiet certainty that you're part of something felt but not seen. That's not proof, but it's a kind of resonance. So tonight, imagine your body not as a separate thing, but as part of an entangled web. Your breath syncing with distant waves, your heartbeat echoing something older than time. You are not alone, not in the science, not in the silence. Nature may already know the quantum rules we're just beginning to name. So sleep softly in that knowing. The robin still flies, the leaf still listens, and the world, strange and silent, is still deeply connected. You're floating now through time as easily as you've drifted through space, and as your thoughts grow lighter, the lines begin to blur. Up becomes down. Distance loses meaning, and now, gently, you arrive at a question that feels both wild and inevitable. Can quantum entanglement stretch across time, not just space? If particles can be entangled across distance linked beyond the reach of sound or light, could they also be entangled across past and future? Could something you measure now affect something that happened before? This idea isn't just a bedtime fantasy. It's part of a real and growing discussion in quantum physics. Let's start small. Imagine two particles, A and B, that were never entangled at the same time. They never met, never interacted. One is created in the morning, the other hours later in the afternoon. But then you do something curious. You send each one into a system that does contain entangled particles, and you perform just the right measurements. Suddenly, A and B show correlations as if they had been entangled all along. This is called entanglement in time. And yes, it's been tested. In carefully crafted experiments, Physicists have found that entanglement can appear between particles that were never alive at the same moment. One comes and goes, the other is born later. But still, they match. Still, they know. It's unsettling, but also beautiful, because it suggests that cause and effect may not be as rigid as we thought, that the future might reach back into the past, brushing its fingertips across choices already made. Here's your science fact to rest beside your pulse. In 2013, researchers at the University of Jerusalem published an experiment showing temporal entanglement between photons that existed at different times. The results matched predictions of quantum theory but challenged our usual sense of when things happen. Time, it seems, is negotiable. But let's go one step softer. If the universe allows entanglement across time, what does that feel like? Have you ever had a moment that didn't make sense until years later? A decision you made long ago that only now reveals its shape? A feeling you couldn't explain at the time, but looking back, it fits perfectly? Maybe those moments weren't random. Maybe they were entangled across time, quiet threads, connecting what you couldn't yet understand to the part of you that would. It's not that the future changed the past. It's that both were always connected, waiting for you to notice. And here's your odd fact of the night. In some interpretations of quantum theory, like the two-state vector formalism, a particle's present state is influenced by both its past and future. One wave function travels forward in time, the other backward. They meet in the middle right where you are. It's strange, but maybe not so strange for you, because memory already feels like this. We reach back and pull pieces forward, but we also reach forward, dreaming, fearing, imagining, and those dreams ripple backward, shaping how we move now. The past doesn't just echo forward. The future calls backward too. And yes, scientists still debate whether entanglement in time is real or simply a mathematical artifact, a clever trick of equations with no physical meaning. But the fact remains, the correlations exist. The math works. The questions remain open. So tonight, drift inside this soft idea. That time isn't a line. It's a web, a field, a fabric. And your moments, your choices, your thoughts may already be stitched together in ways you can't see. Maybe something you've done tonight will make sense years from now. Maybe someone you haven't met yet is already part of your story. Maybe the feeling that you've been here before is just quantum déjà vu. You don't need to solve the paradox. You only need to feel its quiet pull like a thread tied loosely around your finger, tugging softly towards something that's already waiting for you. Rest in that pull. The past is listening. The future is calling. And you, right now, are exactly where you need to be. You've traveled through space and time, traced threads of entanglement and felt their quiet pull. Now, in this soft moment between wakefulness and dreams, you turn inward and ask a tender question. Are you already quantum? Not just made of atoms, of course you knew that, but entangled, connected, even now, to particles and people, places and moments you thought were gone? The answer is a whisper. Your body is a universe of particles, each born from cosmic collisions, ancient stars, and the endless dance of matter and energy. When you touched a loved one's hand, when you breathed the same air, when your eyes met, even briefly, you shared more than a moment. You shared particles, exchanged photons, created new entanglements. Some of those particles are still inside you. Some of that entanglement still lingers, woven quietly through your cells. It's not magic. It's physics. And it means that you, as you lie here, are a walking, breathing, entangled system. You carry memories, not just in neurons, but in quantum connections. Maybe that's why certain feelings sneak up on you without warning. Why a song from years ago brings tears. Why a scent shifts your mood. Why a stranger's smile feels like home. Because entanglement isn't just about particles. It's about relationships. And here's your science fact to hold gently. Experiments have shown that entanglement can survive in surprisingly complex systems. Ions trapped in electromagnetic fields, photons bouncing in tiny cavities, and even in some biological molecules. While the scale of entanglement inside living beings is still under study, the physics says it's possible. This means you are part of a vast, intricate web quantum threads connecting you to the world around you, past and present, near and far. And here's your odd fact of the night. Some scientists speculate that even your thoughts may have quantum roots. The field of quantum cognition explores whether quantum principles like superposition and entanglement might explain how you make decisions, hold multiple possibilities, or experience intuition. Though speculative, it's a humbling thought. You, a quantum storyteller, entangled with people you have never met, bound to moments that shaped you long ago, linked to stars that burned before your first breath. And yes, scientists still debate the extent to which entanglement plays a role in biology and consciousness, but the possibility alone invites awe. So, as your breathing deepens and the edges of sleep close in, remember this: you are not separate, not isolated, not alone. You are a constellation of quantum connections, stretching invisibly but undeniably across the fabric of existence. And in that, you are infinite. Let that feeling settle like stardust on your skin. You, quantum and whole, ready to dream.